So this is the only complication that appears at the boundary points. You notice that the contribution from node 2 was 0. So similarly, you will find that the contribution from interior nodes becomes 0. Okay. So what you are left with is just this contribution from the endpoint. So now let us go back to this equation that we have over here. First term u1 u2, second term u1 u2, right hand side is going to give me one more u1 and some constants, right. So in equation form, what will I write it as? I will maybe you can write it over here now. So the first equation it gave me some term a11 u1 plus a12 u2. Did I have any u3 and u4 terms? No. And did I have a constant term on the right hand side? That is my first equation. Okay. Now let us do testing with T2. Okay. So we have to test with let us say weighting function 2. We did with weighting function 1. Now we have to do with weighting function 2, which is T2 x. Okay. And that will give us a general idea. So now we will look at the first term minus w prime x u prime x dx. Okay. Then I had a k squared wx ux dx is equal to something endpoints. Okay. So minus, let us write it properly. All right. So now this is what we are setting. So now I am going to put, so now T2, and so T2, what is the domain of interest for T2 where it is non-zero? E1 and E2, right. So this is E1 and E2. Okay. So W prime is going to be what? W prime in this segment E1, E2. So it is going to be plus and then minus, right. So this will split into two terms. So there will be a integral minus over E1. The derivative here is positive 1 by delta for W prime. U prime, which terms will appear? Go back over here. U1, which two terms will appear? We are integrating over E1. This is your expression for U. U1 will appear and same as before, right. So what will I have? Minus U1 by, right, minus U1 by delta plus U2 by delta. This is the first term plus, sorry, minus, because the integration is continued over the second segment. I am only writing the first term of the integral. What is the derivative now? Minus 1 by delta, that is W prime. Okay. What appears now? Minus U2 by delta plus U3 by delta dx. Now let us take the next term. So what happens over here? Again I have to do the integration over E1 k squared, right. Now this Wx is, as I have written it before over here, it is going to be n11, sorry, not n11, n12, right, x and u of x over E1. So, both of these terms will come from here as before, right. U1 n11x plus U2 n12x first term, and another term which is coming from integration over E2 k squared. What term will come now? This is segment 2 element 1, I mean shape function 1. What will come now? So, this is 1, 2, 3, 4. So, now I am in segment E2. So, what are the two things that will come? U2 n element 2 left one plus U3 element 2 right one. This is the second term, okay. And then this third term over here, what happens? Wx ux, so it will be a minus, Wx is T2x u prime x at node 2 minus node, sorry, what will it be? Node 3 and 1. Yeah, node 1 minus node 3. Fine. What will this be? What is the value of T2x at node 3, at node 1, let us say? 0, right. This triangle, this green triangle is starting from node 1, going to node 2 and then going to 0 at node 3. So, at both the node points, what is its value? 0. So, very easy. So, you notice that this right hand side term comes into play only at the endpoints, because it gets cancelled like this. This is a clever choice of basis of testing function also, right. Very good. So, now having done this, the second equation becomes, so notice this first equation over here, what all variables does it have? U1, U2, U3, and they are all constants as a function of x. Integrating them is trivial. Second thing, quadratics with k, okay. So, it can be done by quadrature. What variables does it have? U1, U2, U3. Is there any U4? Negative, right. So, this second equation over here becomes 0 times A21 U1, A22 U2, A23 U3 plus 0 is equal to 0. So, exactly, now let us see the pattern. Third equation, so it will be 0 plus A32 U2 plus A33 U3 plus A34 U4 is equal to 0, and fourth equation will give me 0 plus 0 plus A43 U3 plus A44 U4 is equal to B4, right. Now, the right hand side, when I choose my N2 over here in the final equation, its value at the endpoint node is 1. So, that is why I get a non-zero contribution over here. So, all of this put together is going to give me AU is equal to B, and I have a non-zero B, therefore, I will get a non-zero U also, right. So, this in a nutshell is the method by which we solve this FEM in one dimension, okay. So, is it clear what we did? So, remember our starting point was the weighted residual form, we converted that to the weak form. After converting to weak form, we substituted the form of the unknown that I want to find out in terms of shape functions. The only little bit of cleverness I did is I chose my testing functions nicely, so that I got enough equations in variables. So, the endpoint shape functions I left them as it is, and then whatever had a common node I combined those shape functions. That gave me T2 and T3, these triangles, and that is one concept. The other concept was the boundary condition. I have the radiation boundary condition makes sense only for something which is truly supposed to be outgoing. And what is truly supposed to be outgoing? Scattered field, because E incident will enter from one place and exit from another place. So, we should not apply any boundary condition on that, let it do its own thing. We applied on the scattered field, and how do we get the scattered field? U total minus U incident, right. So, that is what, this is the sort of crucial concept over here, right. So, that gave me a condition for U prime, basically that is what I wanted, and that U prime is what I substituted over here, and that gave me a non-zero right hand side, right. So, you can see all the incident field terms are going to appear here. So, trivial, you can see if there is no incident field, there is no scattering. B is 0, U is 0, as you expect. So, that brings us to an end of the 1D FEM equation. You cannot use pulse basis functions because they do not satisfy the boundary conditions that we have. Yeah, the first equation is E1, second is E2 and E3. Sorry, E1 and E2, the next is E2 and E3, and the next is E3 alone. But I mean, that came because of the domain of T2. T2 existed over 2 elements, that is why I had to choose those 2 elements. So, one exercise which you should do is go back and try to use the 6 shape functions and derive this. You will get 6 equations and try to see how you actually, they are basically only 4 equations. It's a very simple exercise. It will give you a little bit more clarity on the thing. Okay, I have given you the direct shortcut, and the reference book, for example, which is chapter 3 of this book by Volakis, they do not do the shortcut. They go through, get a larger system of equations and then do some algebra to reduce it further. What is the complexity of solving this? So, in this case it happens to be tridiagonal. In general, it is a sparse system of equations. So, if you were to do LU decomposition to solve this, the complexity is simply order W times N. Oh, I should not use W. What other symbol will I use? A, B, C, D. Okay, D. D has not been used. D. D is number of diagonal elements. Okay. So, those of you who have done linear algebra, you know that when you have only D number of diagonal elements, then when you start doing LU decomposition, you do not have to do row eliminations many times. You start getting zeros very quickly, only D times you have to do. So, that is why it is order Dn. Typically, D is very small, D is 2, 3, whatever, and compared to N, which is much large, thousands, 10,000s. So, you will not find this order of Dn written anywhere, you will only find it as order N. Right. So, compare this with MOM, which is order N cube, that is why this is fast.